In this video, we're going to be talking about the definition of functions. We're going to be looking at how we can identify whether some relations or graphs are functions or not. Then we'll get into using some function notation, evaluating functions, and we'll leave off with this thing called the difference quotient. So let's see how it goes here. A function is a relationship where an input corresponds with only one output. So for example, in part B here, it's a little hard to see in the video, but I'm sure on your notes it looks much better. Each of these input values is only going towards one of these output values. It's okay for two input values to share an output, but it's not okay, for example, for an input to have two different outputs. So in part A, we can see the difference there. 8 says that it's corresponding with these two outputs. That's not possible as far as functions go. So we say, no, that's not a function, but part B is a function. We could look at that using some coordinates or a data table. If we're doing that, we're looking at the inputs here and making sure that we don't share any of our inputs or that they're not stated more than once. It's okay, again, for those outputs to be stated more than once, but not the inputs. So yes, these coordinates would give us a graph that is a function. In part D, so we're looking on that input spot, and we see a repeater right there. So point 3 has two different outputs. It's got 0.6 and 0.7. That's not a function relationship. And one last time, there is a cheat. If we're looking at a graph, we can use what's called the vertical line test, which means that we draw a vertical line through our graph. Draw it a few times, don't just draw it once, and make sure that that line is only crossing your graph once. So in this case, passing through that absolute value function, we're only hitting it once anytime we draw a vertical line. Whereas in part F here, we can see that if we draw a vertical line anywhere on the circle or inside the circle, we're hitting that graph once and then twice down at the bottom again. So a circle is not a function, or any graph that does not pass the vertical line test is not a function. So that's how we can identify functions. Let's practice describing and using function notation. In the past, your math class maybe had graphs represented by things like the slope-intercept form here, where we use a y for an output and we use an x for an input. As we get more advanced in math, we stop using that y and instead we use a function name. For instance, this function's name is f, and if we put that together by stating what the input variable is right next to it in parentheses, that whole symbol right there, everything right there represents the y value or the output. Not just the f is just the name, not just the x, that's the input variable. But if we put those together, that represents the y value or the output value. So we just replace y with f of x, for example, although we can change the name and the input variable. I'll show you that in a sec. So if you have your function notation instead of y, it will still equal the equation. The equation won't really look any different than what you're used to. So let's compare these three functions and let's see what we notice here. Hopefully you notice that each of them has a name, each of them has an input variable, and in the equation that variable matches that input. But I hope you also notice that these are all three the exact same equation, just using different variable names. So if I was to graph all three of these, I would get the exact same graph. They're the same thing. So all that changed is the function's name. We can use f, that's definitely the most basic one. But we can get fancier. Maybe we get tired of using f, so we'll call a function g. We can do that all day long with any letter we want. The input variable letter could also change. X is definitely more typical, but as we get more advanced in math, sometimes we get bored and we use something else. A lot of times t will be used for time, and then sometimes we use s for a position. Spatia is where it comes from. So we can always change the letters of our function name or input variable, but that doesn't change the actual equation. Let's practice using those functions and practice evaluating some inputs here. When we evaluate a function, the function notation changes. We're told what function we're looking for, we're given the name, and then we're told what input to plug in into the input spots. So you plug that input into any space where you see a variable representing an input. So if we're looking for the f function, well, both of these are called f, so it really doesn't matter which one we use. We're plugging -1 into the input spots. So I plug a -1 into this x, and I plug a -1 into this x. So I'm squaring -1, then I'm multiplying -1 by -4, and then we're adding 7. So -1 squared is 1, -4 times -1 is 4. If we add 7 to all that, we get 12. So write a complete mathematical sentence here. Let's say that f of -1 is 12, or function f is 12 given an input of -1. Lots of ways that we can talk about it. Let's do another one here, g of 3. So we're looking for the g function. So find your g function and plug the input into all the input variable spots. So I'm going to do 3 squared minus -4 times 3 plus 7. 3 squared is 9, -4 times 3 is -12. Adding 7 to that gives us 4. So g of 3 is 4 is how we read that. Plugging numbers in, I hope, is a little basic. What happens when we start to do crazy things like plug an expression in or plug in multi-terms into our function? Same exact thing. Whatever the input is described as is exactly what gets plugged in to your input spots. So I'm plugging x minus 1 into the input spot and squaring it. I'm plugging x minus 1 into the variable right after -4 and multiplying by -4. Let's see how that happens. Let's do a little review here with squaring binomials here. Whenever I square a two-term expression, that's called a binomial, two numbers, two terms. When I square it, there's a pattern that we can use. If I square the first term, I get x squared. If I multiply my two terms and double it, I get my middle term. So x times -1 is -x, and if I double it, I get -2x. And the last step is to square the last term. So -1 squared is +1. If you don't remember that pattern, then you're going to have to rewrite a square by rewriting it twice, and then using that FOIL trick. All right, so hopefully we remember our patterns and we get better at that. Next step, let's distribute right here. So -4 times both of these things inside. -4 times x is -4x. And -4 times -1 is +4. Bring that +7 down on that last step. And we'll finish it off by combining some like terms here. We got x squared minus 2x plus 1 minus 4x and plus 11. So combining our like terms here of 4 and 7. The last step, combine your x terms here, -2x and -4x. That gives us -6x. And the 1 and the 11 are going to combine to give us that 12. So we're bringing everything down. We got our x squared, our -6x there, and the 12. Always rewrite polynomials in order of their exponents, highest to lowest. All right, let's do another one, but this time we're going to look at a different type of function. This function is called a piecewise function because it's just pieces of graphs. We have a piece of a quadratic, and we have a piece of a linear function all together on one graph. So because we have pieces of graphs, it's called a piecewise function. The way that piecewise functions work is that we draw the graph, or graph it, graph an equation, for any x values that are described. So we'll always have some sort of domain listed here telling us that we need to plug those values in if they work. So for example, if my x value or my input is less than 0, I'm going to use this top equation to evaluate it. However, if my input or x value is greater than or equal to 0, then I'm going to plug it into the bottom equation. So these domains describe which equation you use based on the value of the input. All right, so we got x equals -1. I look over here, which one do I use? Well, -1 is less than 0, so I'm going to use that top equation to evaluate. Plugging the -1 into the x spot, we're going to do -1 squared plus 1, and we get 1 plus 1 is 2. Taking a look at another input value, 0. Checking my domains here, it says that if it's equal to 0, then I'm going to use the bottom function. So plugging a 0 into that x spot gives me 0 minus 1, which is negative 1. And lastly, if x is 1, well, that's a value or an input that's greater than 0. So I'm still going to use that bottom equation. So plugging the 1 into the x spot gives me 1 minus 1, which is 0. So that's how we use piecewise functions. All right, one last thing with function notation. Let's bring it to a graph. How can we evaluate function notation? By looking at a graph rather than doing it algebraically like we just did. Well, remember that this is saying what is the output. This is the symbol for output. So this is saying what is the output if 3 gets plugged in, or if 3 is the input, what is the output? So let's go to our graph. The input is an x value, so we'll find 3. We'll trace it down. Where does it hit our graph? Where would it be on the graph? That y value is our output. So scrolling over to the y-axis, we see it's about negative 3. Same thing on the next one. This time if the input is negative 3, what's the output? So let's find negative 3 on the x-axis. Trace it till it hits your graph. And then go over to the y-axis for the value. It's about positive 3 there. One more time, if the input is negative 1, what's our output? Find negative 1 on the x-axis, hit your graph, find out what the y output value is. It's about 3.8. If you're approximating, give it some squiggle equal signs that represents approximately. And as long as you're anywhere within the ballpark, of course I'll try and give it to you. All right, let's flip that question. What if we know the output? So this is saying the y value is negative 2, or the output is negative 2. So what is the input that gives us that y value or that output of negative 2? Well, let's find negative 2 on the y-axis. Notice that the graph is getting that value 3 different times. Here it has an output of negative 2, here it has an output of negative 2, and here it has an output of negative 2. So let's figure out what the x values are that gave us that output of negative 2. Right here, if we trace it up to the x-axis, it's about 3.7-ish. Here, the input that gave us that output is about 0.5, right in between 0 and 1. And then lastly, the input that gave us this output right here, about 3.2. One more time, let's do the exact same thing. If our output or y value is 0, what are the inputs that gave us that? So now, an output of 0 is the x-axis. So where does the graph cross the x-axis? What input value or x value? Well, it does it here at about 3.5. Sorry, negative 3.5. It does it here at about 0. And then it does it again here at about 3.5. So there's function notation looking at a graph. All right, last thing we're doing, we're evaluating this thing called the difference quotient. 2 ways the difference quotient could be written. It could be written using an h in these 2 spots, or some other textbooks or more advanced textbooks start to use a delta x. And that's a little bit more confusing because that kind of looks like there's 2 symbols there, but really that's just one term represented by those 2 symbols. So that gets a little complicated. So at the beginning here, I do like to start off by just using the h's so that we have less of a mess in front of us. If you know calculus and you know your power rule, there's actually a cheat you can use, but I'm not going to use that in this video. If you're interested, I do have some power rule derivative videos that you can watch to learn that. All right, we're going to evaluate the difference quotient. We're going to go the long way. So what the heck does this mean? This means that, first of all, we're going to evaluate the function that's given to us by plugging in x plus h. So very similar to this example right here where we had to plug 2 terms into our input spot. The exact same thing's happening down here. So this is our function. We're told this is our f function. So in the f function, we're plugging in x plus h into this x spot and this x spot. So we have x plus h squared minus 4 times x plus h plus 7. That's just substituting the first half of this numerator. Next, we're going to subtract the original function. So this is our function right here. We're going to subtract that whole expression right there. So if we're subtracting more than one term, let's make sure that we put it in brackets or parentheses. And that reminds us that when we subtract a big expression, we got to distribute our negative to each term. So when we distribute or multiply by -1, what we're essentially doing is making everything the opposite of what we see. So instead of x squared, we're going to have -x squared. Instead of -4x, we're going to have +4x. And instead of +7, now we're going to have -7. All right, so that takes care of the end part right there. Let's go back to the beginning where we had to square that binomial again. Using our pattern, we're squaring the first term and getting x squared. We're multiplying our two terms here to get xh and then doubling it to write 2xh next. And then we're squaring our last term and writing h squared last there. Distribute right here in the middle, we got -4 times x and -4 times h for -4h. And we got that +7 at the end. All right, so now we have this big, long statement up in the numerator position. We're going to start to combine like terms and see if we can simplify some things. And we're still dividing by h. Keep that going on the bottom. We have an x squared. Well, we also have a -x squared, so those are going to cancel. We don't need to bring them to the next step. We have a +2xh, no -2xh's, so we are going to bring that down to the next step. We have a +h squared, but no -h squared, so we're going to bring that down to the next step. And we have a -4x next, but we have a +4x here, so those two things are going to cancel. That's cool. Next, we have a -4h, no +4h's, so we do have to bring that down to the next step. And lastly, we got a +7 and a -7, so those are going to cancel, and we're done simplifying and combining like terms. Whew. It's getting tough here, but this is where it gets nice. Because if you notice, all of the terms up here in the numerator now have an h. We can factor the h out of them. So taking the h out of that first term, factoring it out, writing it at the front of the parentheses, that leaves behind 2x. Factoring an h out of h squared is going to leave 1h behind. And then factoring an h out of -4h is going to leave -4 behind. Now, this is important right here. We want these h's to cancel. Because we're multiplying by h and dividing by h, they will go away and become 1. Be careful they don't become 0 or just disappear. They become 1. And then we write our leftovers. We got 2x plus h minus 4. You can also reorder that to say 2x minus 4 and then put the plus h last. All right, so that's a big problem, a lot of algebra steps. But there it does, it works out. We can get a little simpler version of it. Little heads up right here, if you get to this step right here, if you find that you have other terms that don't have an h in it, then you may have made a mistake, because for that last step, we always want to just have h terms so that we can factor it out. So if you get to this step and you realize that you made a mistake, then check your work up here on these two previous steps. Definitely tons of room there to make a mistake. Always get to a step where you just have common terms so that you can factor it out and get rid of that dividing by h on the bottom there. All right, we got one more. Go ahead and pause the video if you want to try it on your own, and then come back. Here's the explanation. We're doing the exact same thing, except that our function is slightly different. So we're plugging the x plus h into all of our input spots first, and then finishing it off by subtracting 3. That's the first half of the top. Don't forget the second half. We got to subtract the original function. So subtract and rewrite the original function in parentheses or brackets. Don't forget to distribute that negative to each of those terms. Squaring that binomial gives us x squared plus 2xh plus h squared. Distributing right here gives us 2x plus 2h. Don't forget that minus 3 there. And distributing into that expression gives us -x squared minus 2x plus 3. We're still all over h. Remember, we're trying to get down to just terms with h. Let's see if it works out. X squared and -x squared are canceling. We're left with 2xh. Good. H squared, nothing to cancel with. 2x and negative 2x canceling. 2h is coming down. That's good. It's still an h term. Negative 3 and positive 3 canceling. And that's everything left over. So we got everything with h's in it. We'll be able to factor the h out. Factoring it out from the first term leaves behind 2x. Factoring it out from the second term leaves behind h. And factoring it out from that third term leaves behind 2. Cancel your h's now and rewrite the leftovers for your final answer. 2x plus h plus 2 or 2x plus 2 plus h. Alright, so there's a good video about some function notation. What is a function? How do we look or evaluate functions on a graph or algebraically?